Okay, so this is the last video for the Unit 4 playlist. We are talking about what are called molecular shapes. When we say the word molecular, you need to think of covalent bonds. A molecule is something that is covalently bonded together, so we're going to practice more covalent structures and then determine how they will look in real life. Okay, so molecular shapes are determined by what is called a VSEPR theory. The VSEPR theory stands for the valence shell electron pair repulsion. So when we're talking about valence shell electron pairs, these are the electrons that are involved in bonding. And so the key word is that repulsion. Electron pairs want to be as far apart from each other as possible. That's because electron pairs are negatively charged. A negative does not want to be close to a negative because same charges do not attract. So because of that repulsion, that causes molecules to have particular shapes. So let's look at the example of that. So there are some steps that you need to follow in order to determine the shape of a molecule. So there are only 4 steps, so you need to copy these down. Very first thing you need to do is draw the Lewis structure. So you're going to follow the same steps that we learned for covalent Lewis structures and draw what it's going to look like on paper. Once you've done that, you're going to count what are called the clouds around the central atom in that structure. A cloud is any bonds that are off that central atom. It could just be a single, double, or a triple bond, or an unshared pair of electrons. So count up the number of clouds around it, and then you're going to look at the chart that I'm going to give you in class tomorrow. And then the final thing that you're going to do is determine if the shape is polar or not. And this can usually be determined by looking at the chart that I'm going to give you. So here is the molecular shapes chart. So if you notice going down this side here, you're going to first count the clouds, and then based on how many they have, you can see what the possible shapes are going to be. So if there's only 2 clouds, there are only 2 options for the shape. It's either going to be linear triatomic, meaning 3 atoms, or it's going to be linear diatomic, meaning 2 atoms are involved. So whichever one it looks like the most is which one you're going to pick. If it's got 3, it's either going to be called trigonal planar, which means it's a central atom with 3 atoms connected to it, or it's going to be bent, which means the central atom has only 2 things off of it, but it has an unshared pair of electrons. If it's got 4, there are 3 options. Tetrahedral means the central atom has 4 different atoms off of it. Pyramidal means it only has 3 atoms connected to it, and the 4th thing is an unshared pair of electrons. And then bent means there's 2 things off of it with 2 unshared pairs of electrons. Now if you notice underneath each one, it tells you how to determine if they're polar. So for example, a linear diatomic, you just have to determine the polarity based on the scale from the covalent bonds video. If it's pyramidal, it tends to most likely be polar. So you can use this table to determine not only the shape, but also the polarity. And there are a couple notes about the polarity over here, so we're going to use these in class when you practice these on your own. Okay, so determining if the bond or the shape is polar. So there are 3 steps in order to do that. The very first thing you need to do is determine if the bonds are polar. Remember, all you have to do is get the difference in the electronegativities of the elements that are involved and just see where it falls on the scale that you have from the covalent bonds video. The next thing you're going to do is, if it is a shape that tends to be polar, the polar bonds will not cancel each other out, and we'll look at an example of that on the next slide. And then if you're in doubt, just use the chart. It'll tell you if it's most likely going to be polar or non-polar. So let's work out one example of covalent bonds. Okay, so this is an example of a covalent compound. This is H2O, aka water. So remember, the very first thing you're going to do is count the total number of valence electrons. Each of our hydrogens has 1, and then oxygen has 6. So we have 8 valence electrons to assign. Oxygen's going to go in the middle because hydrogens never get to go in the middle. Connect with the bonds. I've used 4 of my valence electrons and I have 4 left. Can't put them on the hydrogens because they only need 2. So I'm going to place those on the oxygens, and that means oxygen is now going to be happy with 8. So now, once we've drawn our Lewis structure, now we need to count the number of clouds around the central atom. So remember, clouds are either a bond or the pairs of electrons that are not involved in the bonds. So if you look at our oxygen atom, it's got 2 unshared pairs, and it's got 2 bonds off of it. So total, it's going to have 4 clouds coming off of that central atom. So let's look at our table and determine what the shape is going to be. Okay, so we have 4 clouds that are coming off of our Lewis structure. And so we need to look at the 3 different options and see which one it fits the most. So it can't be tetrahedral because there are actually only 2 atoms coming off of our central atom, so it can't be this one. Pyramidal, it needs to have 3 atoms attached to the central atom, so that's out. So that leaves us with the very last example, which is bent. Bent is going to have 2 unshared pairs, and that's what we have on our oxygen atom, as well as 2 different atoms attached. So this matches, and it says that the bond angle is 104.5 degrees. So what's going to actually happen is this is what we have it on paper. But in nature, water actually has this shape right here. And what's happened is that these unshared pairs need their own space. And that's going to push these 2 hydrogens down at a funky angle in order to create enough space in between all of the electrons around that oxygen. Take note that it says that it's usually polar, so we're going to look at that a little bit closer by determining the polarity of each individual bond. So let's draw this correctly now that we know the right shape. Okay, so now that we know the correct shape, we're now going to draw the oxygen atom. The 2 unshared pairs are going to have either side on the top here. The hydrogens are going to be bent down at an angle below it. Okay, so this is the actual shape of water. And so let's look at the actual individual bonds. So we have a bond between oxygen and hydrogen. So if you have the electronegativities, which I will provide to you, oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. So all you need to do is get the difference between these 2 numbers, and that's just a difference of 1.4. So this falls on the scale as polar. So what you have is a polar bond, meaning this oxygen atom is pulling on these electrons, and it's causing those electrons to be a little bit closer to the oxygen atom and depriving these hydrogens a little bit of those electrons. So what you have is a dipole. You draw the dipole over to the side like I did here. It points to the negative end, and the positive end you just put a little slash through it. So you can see there's a little plus here to represent the positive, and then it points towards the negative end. Why is the end up here negative? Well, if you're pulling electrons closer to the oxygen atom, and it's got these unshared pairs next to it, this oxygen atom is going to have a lot of electrons around it, so it's going to tend to be more negative. And then the hydrogens are being deprived of those electrons, so it's going to be a little more positive. And so that's how you figure out the shape and the polarity of a molecular compound.